Now that you know how to classify different types of bonds, we're going to talk mostly about ions, how they form, and ionic bonds, and then how we name those things. That's one of the big struggles, is how do you take a formula and name it, or how are you given a name and actually write a formula for it? So let's kind of dive in here. So we've learned this already. An atom that has gained or lost an electron forms an ionic bond, but it by itself is called an ion. And there's different kinds. So the goal of any element or atom is to kind of have that magic 8 valence electrons. It wants to have a very full outer shell, and that's why we have what we call the octet rule. And that's where elements like to have that 8 electron configuration in their outermost ring. There is one exception to the rule, hydrogen, because it only has 2 electrons, so it likes to have 2 in its first shell. But everything else likes to have 8. And so depending on where an element might fall in the periodic table, it will either be easier to gain some electrons to get up to 8, or lose some electrons to get kind of down to 0, which means their next level has a complete set. So atoms that steal electrons are the more negative ones. Electrons, if we remember, are negatively charged. So when you take them, you become more negative. And they are called collectively anions. So thinking about anions, they're labeled here at the top. Chlorine has taken 1 valence electron. Oxygen has taken 2 valence electrons, and fluorine has taken 1. And how do I know that? It's designated by a little superscript. If there's not a little 1, but instead there's just a negative, then that means that it's a -1. Or it could be a +1 too, as we'll see in a minute. Otherwise, you'll see a designation of a different number. And since elements can have anywhere from 0 to 8 in their outer shell, they can gain a certain number. But if we gain electrons and become more negative, we're anions. I always think like an is anti or against or negative. Now, on the flip side, there are atoms that are going to lose valence electrons because it's easier to lose them than try to gain 6 or 7 if they only have to lose 1 or 2. So those ones become positive, and those are called cations. Think of cats have paws. Cats are positive. And you see that designation over here with sodium that will lose 1. So when you lose an electron, you end up becoming a little bit more positive. And calcium will lose 2, and aluminum ends up losing 3. And that's just easier, for example, than aluminum trying to gain 5 electrons to get to that magic number of 8. So there are some elements that have kind of 4 valence electrons. So it's kind of a 50-50 split of gaining 4 or losing 4. But when we look at the periodic table, if I zoom out a little bit, there we go. You can see anything in this first column has 1 valence electron. So it's very easily going to lose that one and therefore become +1. Anything that's in the second column has 2 valence electrons. So it's pretty easy for them to lose 2 than try to gain 6. And oftentimes these are always going to be your +2 ions. Then you kind of jump over to this column right here. You skip all the pink ones in the middle, the transition metals, and you jump over here. These are all going to be +3 because they have 3 valence electrons. These are the ones that are 4, so they can kind of go either way. And then you go the other way. These ones have 5 valence electrons. So for them, it's going to be easier to gain 3 than it is to lose 5. So this row right here, if I mark on it, let's see if I can. So let me kind of go back and show you. These ones will be the +1s. These will end up losing 2, so they'll be +2s. These will be the +3s. These are the 4s. They're like a 50-50 split. These ones are going to end up gaining to get to that 8 number. These ones have 6 valence electrons, so they really only need to gain 2. And these ones have 7 valence electrons. They only need to gain 1. So that's why we get this distinction. And since they're negatively charged again, you get a negative symbol out front if you're gaining electrons and positive if you're losing electrons. This last row here in column 18, I said row, but I meant column, is containing the inert gases. This group here has 8 already. They don't need any more. So because of that, they are kind of happy as they are. As we saw in a previous video, they don't like to react. They don't want to gain anything. They don't want to lose anything. They already have their magic number, so they like to just hang out by themselves. So just kind of thinking along the lines, if it's helpful to write these above your periodic table, then please do so. Okay, so kind of coming back over here, moving right along. Atoms that have more than 4, as I mentioned, want to fill their outer shell. So those are going to be your anions and gain. Atoms that have fewer than 4 are generally going to lose electrons. So those are going to be your cations, the positive ones. So let's do a little bit of practice. Thinking about your periodic table, which hopefully you have in front of you. Sodium is element number 11, and it is abbreviated by Na. Since sodium, if I flip over, is in column 1 here, it's going to have 1 valence electron. So that would give me 1 valence electron. So because it only has 1, it will lose that 1. And if it's losing an electron, it's going to become a little bit more positive. So you can write cation or put positive. So overall, it will become Na, and then if it helps, you can put +1. Otherwise, you just have to put plus. So now let's take a look at calcium. If I come over to the periodic table, calcium is number 20. It is in the second column. So again, these are the +2s. So calcium as a symbol, I will write Ca. It has 2 valence electrons. So because of that, it will lose 2 and become positive. And oops, let's try to erase that. That wasn't good. You would write it as Ca, and you can do 2 plus or +2. It doesn't much matter. Aluminum is over here, number 13. This is the +3 column. So just kind of continuing on in the trend here. Aluminum's symbol is Al. It has 3 valence electrons. So we haven't quite hit that tipping point yet of trading from losing to stealing. But now we get to one called chlorine. So if we look at the periodic table, chlorine is number 17. It is in the 7th column that we've kind of referenced, or has 7 valence electrons. So for it, it's going to be easier to gain 1 than it is to lose 7. So it's going to gain 1, and because of that, it becomes negative. It only needs 1, so in reference, we'll just put a Cl-. If it helps to put a 1 there, you can put a 1 there. Oxygen is number 8. It has 6 valence electrons. So when we're thinking about how we might do that, it's going to be easier for it to gain 2 than do anything else. And as a result, it is going to become negative, and we would just put O minus 2. And last but not least, we have hydrogen. Hydrogen has 1. It will lose 1, become positive, H+. So this just kind of goes through how you would normally come about those pieces before we have to try to join them together in compounds. Which brings us to our next slide. To form a compound, you need to put a positively charged thing together with a negatively charged thing. And a key piece of this is the fact that the positive charges and the negative charges are going to cancel. And they are commonly referred to as salts. So the first part of an ionic compound includes cations. So the positive thing always goes first. So this is referred to as a sodium ion. It is sodium and it's lost an electron, so therefore we give it the name ion after its element. Mg, 2+, is magnesium ion. It's in the second column of the periodic table, so it has a +2. Anions, on the other hand, the negative thing comes second. And usually what we do in that regard is just chop off the ending of the normal element and add "ide." So fluorine turns into fluoride. Or in this case, oxygen turns into oxide. So you cut off the end of the word and put "ide." And we will do some practice of this too. I included a chart in here for you because, as I mentioned, the ones that we've been working with and that we have been naming always really behave the same. Na will always be +1. Mg will always be +2. Al will always be +3. And so on. There are elements that are called transition metals. That is groups 3 to 12. That's the pink guys here on the periodic table. Those do behave a little bit differently, and we will get to those because they can kind of have different charges depending on the situation. So let's go ahead and do some practice here as well. Thinking about sodium, we're always going to somewhat come back to sodium. Sodium's symbol is Na. And you could say its name would be sodium ion because that's how we name the positive ones. And its ion symbol would just be Na+. Because sodium is in that first column. So I know that it's going to be a +1 because it's in the first column of the table. So that brings us to, I don't know how to make this little guy go away, aluminum. So the symbol for aluminum is Al, and it's positive, so we would just say aluminum ion. And it is in that third or 3+ column, so we always know that it's going to behave that way. The next one we haven't talked about before. It's neon. It's number 10. It's actually in that last inert gas row, so it's going to behave a little bit differently. Its symbol is Ne, and it's not going to form an ion, and it's not going to have an ion symbol because it is an inert gas. It does not want to have friends and play and share or steal or do anything. It is inert. So because of that, it doesn't actually have an ion. So that was kind of a trick question. But next up, we have sulfur. Sulfur is right here under oxygen, number 16. And therefore, this column has 6 valence electrons. So sulfur's symbol is S, and it's negative. So instead of being sulfur, we cut off the UR and turn it into sulfide because it's the negative or it's the anion. as we're thinking about things, these first two were cations, and we will find that these last two are anions. So these are the ones that are going to have the "ide" ending versus ion. And neon, as I said, was a trick one. So the symbol for this, because it has 6 valence electrons, is going to be 2-, because if it has 6, it wants 2 more. Fluorine is in the 7th column, or it has 7th valence electrons. So its symbol is F. And if I come over here, normally it would be fluorine, and we chop off the "ene" and turn it into fluoride. And since it only needs 1 more valence electron, then I just write it as F-. Okay. So thinking about how these things come together, this is a picture that just kind of shows you how ionic bonds can form. Sodium chloride, for example, Na will give away its 1 valence electron and come over to chlorine. The same thing could be true for magnesium. Magnesium has 2 valence electrons, whereas oxygen, if I were to draw out the Lewis dot structure, it would look something like this. So what ends up happening is Mg will give up 2, and my arrows don't necessarily have to be super awesome here, so that oxygen gets its 8 and magnesium has its only 2. All right, so kind of continuing along here, we can name different compounds. The first one is the metal, and the second one is the non-metal. And in here, we have sodium chloride. So sodium is the first element, and then chlorine turns into chloride. So when we're naming these things too, normally it would be a sodium ion and a chloride ion. We kind of get rid of the ion name. Here we have Ca, which is calcium, and then oxygen. So oxygen turns into oxide. At the bottom, you can kind of see how we name those things. So the charges themselves need to cancel out. So for example, down here, if you have something like Na, or you're trying to combine Na, well, it only has a +1 charge. If you're trying to put it with sulfur, it has a -2 charge, meaning that it needs to take 2 electrons, but sodium itself only has 1 to give. So there's this little crisscross method where basically to figure out how many you need, you just switch the charges and those become your subscripts. So I need basically 2 Nas to satisfy 1 sulfur. Each one of these has +1, so together they make +2, and that will balance out this. So that's what this kind of crisscross method means. If I want to do the same thing for Ba and N, Ba has a 2 charge, or 2+ charge, but N needs 3. So this one's an even crazier one. So what you end up doing is you just crisscross the superscripts. So if I want to make it even, I'm going to need 3 of these and 2 of these. So collectively, you end up with kind of overall 3 of these, you'll have a +6 charge, and 2 of these, you'll end up with a -6 charge total. And therefore, they're balancing out. The last one here is Ti, which has a +4, and then you have oxygen, which has a -2. So normally what you would do is you would just crisscross like so, and you would get Ti2O4. But there is a way to simplify. If I have 2 of these and 4 of these, well, you can easily just kind of divide by 2 and get away with this more simplified version. And that's what they're showing you here. So let's go ahead and do a little bit of practice here to help. So they did sodium chloride for you. So now we're going to do MgCl. So Mg has 2 valence electrons because it is in the second column. If I look at the periodic table, it's in the second column, so it's going to be a +2 always. Cl is in the second to last. It has 7 valence electrons. So similar to right above where I have drawn here, chlorine has 7. So what's going to happen here is, great, this Mg can give one to this chlorine, but now we have a problem. There's still another valence electron. So what needs to happen is you actually need to have another chlorine to complete the balance so that this guy can come over here and you end up with MgCl2. I need 2 chlorines to balance out the magnesium. And one way you could have done it too, if you don't like drawing the Lewis dot structures or you don't feel like that's helpful for you, then do what we did on the last slide. I know Mg is a 2+, I know Cl is a minus, so then you could do that crisscross method that we were just doing and arrive at the same thing. But for drawing's sake, I will kind of keep that piece on there. So aluminum has 3 valence electrons. Actually, I'm going to erase this one and put it on the bottom to make it a little easier. Okay, so it has 3 valence electrons, and I would end up doing my tiny dots here, 7 for 1 chlorine, and therefore this one can come over here. But notice I still have 2 left. So you're going to end up needing to put 2 more chlorines to share here, or give up those last 2 aluminum electrons. So then you end up with a final formula of AlCl3. Again, if it's easier for you, do the crisscross method, and you're going to end up in the same spot, AlCl3. So here is kind of a practice piece that we will go over next time when we continue on.